So we're going to probably just get through conjugate pairs and a little bit of strength of acids and bases. I'm going to ask you guys to make a note card today, and we'll start putting them up on the front bench here like we've done before, just so you can memorize some of that basic information. All right, so we just did our Valentines with acids and bases, so you know a little bit about them already. Acids have a sour taste. You know that from lemons, acetic acid and vinegar. Bases have a bitter taste, so some poisonous plants, people would reject this flavor, broccoli, turnips, baking soda. Bases are slippery, they're soaps. Some interesting stuff about like how biologically you would kind of reject the flavors of these things could be because your body is rejecting the nutrients that those give you. So there's some things about this, which I was going to go into a little bit about how iodine, broccoli, I think it's broccoli or turnips, inhibit iodine getting into your thyroid, and so you need iodine in your body. Some salts, like table salt, has iodine added to it so that you can get additional iodine. But perhaps if you need that iodine, your body would reject the flavor of broccoli and turnips because it's trying to get iodine into your body, and if you eat that, it would inhibit it. So your body, tells you what you need, so that would be one of the ways of doing it is you just don't like the taste of it. So bases feel slippery because they're in soaps. They react with oils in your skin to form the soap. Many cleaning products containing ammonia. Remember, ammonia is not ammonium. Yum, yum, yum has the extra hydrogen. So ammonia products, you know that smell, I'm sure, from cleaning products. And a lot of other products have sodium hydroxide in them. Blood is basic, but it is a buffer. So we're going to get through what a buffer means later, but basically it can accept changes either in pH from acidic or basic changes and then still stay within the same range. And then drain cleaner contains potassium hydroxide, which is a very strong base. All right, so there's two types of acids and bases that we can describe. There's Arrhenius acids and bases, and then the next one we're going to do are Bronsted-Lowry acids and bases. You probably have seen some of the multiple choice questions already. It'll say, like, which of the following is a Bronsted or an Arrhenius, and I usually cross them off because we're not there yet. So an Arrhenius acid and base is the kind of honors chem version of what an acid and base is. Acids have H+, bases have OH, and that's all I've taught you so far, right? So you just identify it by looking for hydrogen or hydroxide. So that's true. Acids will dissociate to produce H+, so either when they're dissolved or when they're molten, basically, like liquid. And then bases dissociate to give you the hydroxide. So that's sort of our general description of them, except there's so many bases that don't have hydroxide, and they're still considered bases, like ammonia. We just said is a base that doesn't have hydroxide, so how do you characterize that? So this is sort of not a great way to characterize them, so we switch with to the Bronsted-Lowry. So this is the same thing that I just said, is that they don't have hydroxide ions. So Bronsted-Lowry acids and bases, the Arrhenius acid definition works for all acids because they have H+. So H+ falls off the acid, means that it gets rid of it. And this is the same as the Arrhenius equation. But for the Bronsted-Lowry specifically is that they pick up H+ ions. So if an acid is donating an H+, the species that accepts the H+ is then considered the base. So always really easy to remember, acids have H+, and then whatever picks it up would be the base. So this works for most of our acids and bases when we're looking at them. All right, so for our Bronsted-Lowry reactions, HA is going to be our general way of describing an acid. A meaning it could be any anion attached to it, and then the H+. Your base we're just going to call B. So anytime that we're doing buffers and titrations or anything, I will use just this general format of HA and B. So we know that this is the acid because it has the H+, and then it's reacting with what we're going to say is the base. On the opposite side of the reaction, you will identify what's called the conjugate acid and the conjugate base. Conjugate just means the other half of it when it turns into the base or the acid. So the acid gets rid of its H+, then its conjugate base is the anion that's left over. The base has a conjugate acid. Once it picks up the H+, it's what's on the right-hand side of the reaction. So you will always have, in any reaction, two acids and two bases, essentially. And we're going to talk about that they go to completion, but what does this double way arrow mean? Equilibrium. It goes in either direction, right? So especially when you see a double way arrow, you're going to pay attention to that pretty much in all of our reactions. If we see a double way arrow, that means that we have both reactants and products. So in this beaker, essentially, we have 2 acids and 2 bases, and one of each is going to be stronger, and that's going to tell us if we end up with an equilibrium system or if we end up with a system that completely creates products. All right, so label these. What is what? So first reaction. Identify this and this. Which one's the acid, which one's the base? Write it on your paper. That should be sort of easy. All right, by default, you'll know what water is because you know what HNO2 is. Can you name HNO2? Remember your acid naming rules? So if it's an ide, it's a hydro and an ic. If it's an ate, it's an ic. And if it's an ite, it's an us. So your NO2 minus is nitrite. So therefore, it's nitrous acid. So that's your acid. Water is your base. So on this side, label your conjugate acid and your conjugate base. All right, so take a look. This was your acid. It donates its proton to hydrogen, to the water. And on the right-hand side, your conjugate base is now able to pick up an H+. Do you see that? That's why it's considered a base, because it could pick up an H+ and remake this acid. Water is a base in this case, and it picks up the H+. When it picks up an H+, this is called hydronium ion. Hydronium ion can be written as either H+ or H3O+. It's the same thing. It's just the acid component in the solution. So H3O+, because it picks up an extra H. And if it picks up an H+, then it carries a positive charge. You have to recognize this constantly as being acidic. All right, so then for our next example here, we look at ammonia. And ammonia will become very familiar with you because we're going to use it constantly. But right now, when you look at it, you're kind of not sure what would this make, right? So recognize that H is a positive. Hydrogen is your proton, essentially. So if I take away an H, pretend you didn't know that this was a base, and you thought, well, maybe this is an acid. If you take that away, then this becomes NH2-, and that's probably not something that you're ever familiar with, right? But if you add an H to this, as if it were a base and it's accepting a proton, then it would become NH4+. That is familiar to you, right? So you would recognize that it could possibly do that. So this is definitely your base, which makes water what? Your acid, and then label your conjugate acid and base on the other side. So you should recognize, again, this is the base, this becomes the acid, this is the acid, this becomes the base. Now notice, in these two different reactions, water is both an acid or a base. It just depends on what kind of reaction it's with. So if you take water and you remove the hydrogen, then it becomes OH-. If you add a hydrogen to water, it becomes H3O+. So water can behave both as an acid or as a base. All right, acid strengths. So we know that some acids are really dangerous and that others are just fine. Like you ingest acetic acid, right? You ingest acids all the time. But you would never go and drink sulfuric acid, right? So there's different strengths of acids, and you're going to have to memorize them and understand them. We'll do that in a moment. But strong acids, when we say something's a strong acid, we're saying it completely dissociates totally into H+ ion and its anion, whatever its conjugate base would have been. If it has complete dissociation, we draw a one-way arrow. This is so important because you will see reactions written and then a whole series of questions about them, and you'll know, based on the arrow, that this goes to completion or doesn't. Now, we know from equilibrium and all of our K values that we've done, right? A K value that goes to completion is what? Greater than or less than 1? Much, much greater than 1, right? Because it has products over reactants, so you're making lots of this. But we still understand from equilibrium that nothing technically goes all the way to completion, right? Like there's always a little bit of the reactants left, but in theory, we're going to draw a one-way arrow. We're going to say all of this goes to completion. So that whatever this acid is, HA, completely gives up that H plus and it'll go over to the other component. If it's a weak acid, we always write the equilibrium sign. So that's another clue. It's a weak acid, and it just basically means that it can go back and forth. You'll have some of the reactants and some of the products, and then we will calculate eventually a K value, except we're going to call it Ka, right? K anything just means products over reactants. So right now you have your Kc, your Kp, your Ksp, and then now we're going to learn Ka and Kb. And they're all the same. They're all K. It's just equilibrium. So two-way arrow tells you that it lies to the left or somewhere in the middle, but it doesn't go all the way to completion. So these are your big six. You must memorize them. So we're going to make a sheet right now. I would get yourself a note card or a piece of paper. I think I have extra note cards here for you. And so you guys can grab these and pass them out, please. And this should just be kind of stapled to all of your homework and every time that you're doing it. So the first one is HClO4. What's the name of that one? That's perchlorate. So if it has an 8, it should end in an ic. So that's perchloric acid. Yep. The next one is HI. What's the name of that? Hydroiodic acid. The next one is HBr. What's that? Hydrobromic acid, HCl. Hydrochloric acid, HNO3. Nitric acid, because it comes from nitrate. And then H2SO4, sulfuric acid. You have to memorize these as your big six. These are the strong acids. So if they're not strong, then what are they? They're weak. As simple as that. So if you know your big six, then you know the rest of them are just going to be considered weak. So I'm going to take these up so that we're constantly staring at them. And if you're lucky, I'll forget to take them down on the test day. I'll have to hang that a little bit higher. All right, so anytime that we're doing a reaction with these, we're going to draw a one-way arrow, right? It means that it completely pulls off its H+. So if I was taking this apart, this would go to H plus ClO minus H plus I minus H plus Br minus. You following how this works? What would you do for this one? 2 H pluses plus SO4 minus 2, right? So technically this is going to produce a more acidic solution because you would have more H plus floating around. If I had 1 molar concentrations of all of these, this is going to dissociate to give me double the amount of moles of H plus. And so when we calculate pH, which we will soon, pH is completely dependent upon how much H plus is floating in a solution. Good so far? All right, strong bases. So you could write on the opposite side, but this is not super hard to recognize. A strong base is anything that has hydroxide with it in a group 1 element, calcium, strontium, or barium. These are our general ones that we say are strong bases. So strong bases are hydroxide with group 1A, and then calcium, strontium, or barium. You got it, jot it down? All right, so again, if we have reactions with this, we're going to have a one-way arrow. So complete dissociation. All right, if it's not a strong, then it's a weak, right? Weak bases, typically, the really easy ones to identify, besides if they're not with hydroxide, right, would be our Bronsted-Lowry acids and bases. And we need the Bronsted-Lowry one because that explains how it's going to pick up a hydrogen. So when you see, and this is sort of more organic based because we don't really draw structures in terms of reaction chemistry. We do reactions, we draw structures, and those are sort of separate in inorganic chemistry, which is what this class is. But in organic chemistry, we make reactions based on the way the molecules look, and they sort of fit the pieces together, and you come up with structures as your product. That's more organic. So what you should recognize is that almost all the time, right? If you have nitrogen in a compound, it's going to have a lone pair. Like if we draw out NH3, it's NH3 with a lone pair sitting on top. That lone pair has the ability to accept a bond, essentially, right? We can accept another component here, which would be hydrogen for us. So if we donate from hydrogen from this water, we donate here, it will pick it up, and then it no longer has its lone pairs. And then the water would give up its hydroxide. So this would be considered, if it accepts the proton, a base. So sometimes you'll be given nitrogen compounds. In general, just assume that they're the bases if they have that lone pair on them. So you might have to look at how many things are attached to a nitrogen. If it's attached with just 3 things, it means it's going to have a lone pair available to accept a hydrogen. So this structure here has a nitrogen, lone pair, picks up a hydrogen. So nitrogen-containing compounds are going to be bases, unless, of course, they have an H+ already attached to them. All right, our strength of our acids and bases. This should make sense to you. If I have a strong acid, like HCl, hydrochloric acid is a strong acid, then its conjugate base is going to be weak. Right? So if it gives up its H+, think about this. This should help you. If I have HCl and I give up H+ and Cl-, and this is a one-way arrow, meaning it completely makes products, right? This acid, and then this is an acid, and this is base. If this base were really strong, it would grab this H+ and pull it back. Because isn't that what a base does? It takes H+, right? So think about it in terms of strength, almost like tug-of-warring. Like it gets rid of something if it's an acid, and it grabs it if it's a base. If this were a really strong base, it would grab this H+, and it would remake HCl. And then this would have to be a double-way arrow because I would be reactants favored. Does that make sense? So this has to be a weak base because if it's weak, then it can't grab this as well as this can kick it off. And then it becomes a one-way arrow and stays to the right. So strong acids always have weak conjugate bases, otherwise they wouldn't be able to completely dissociate. And then a very weak acid will always have a strong conjugate base. And then acids with mid-range strengths have conjugate bases with mid-range strengths. So just depends. So I'll just draw up another acid for you. If I put HF up here, this is a weak acid. I have a double-way arrow. It still dissociates to give me this. But if this is a weak acid, then this must be a strong conjugate base. And that should make sense to you because now this can pull this H+, and it's going to be left side favored. It's going to make the HF. I lost a count. All right, so here are your strength of your acids. You know your big 6, so basically what we're going to say is here's our 2 of our big 6, and then we start with HF, and then we go down to ammonium, water, and this is methane, which methane is not, it's hard to even consider that to be an acid, but technically I suppose it could because it could donate an H+. So it's pointing out to you that as the strength increases, your conjugate base strength increases, and that should make sense. CH3-, that's ridiculous. We would never want to see this, right? We would never see that. And if that does exist, it obviously is going to immediately want to pick up a hydrogen to make that bond, right? So that's why this is such a strong base, and this would be such a weak acid because it would never want to do that anyway. And you know when I say things want to do stuff, I'm just talking about how it's going to give up its hydrogen or accept it. All right, so the stronger base always accepts the most protons in an acidic base reaction. So what I'm talking about is before, when we did our reactions, I said there will always be 2 acids and 2 bases in the solution. You have your acid and then your conjugate acid, and then a base and a conjugate base. So you're basically fighting. You're looking at which one is the strongest, and whichever one's the strongest is going to either drive the reaction to produce all products, which is a one-way arrow, or if your right-hand side is stronger, it's going to drive it to the left and create more reactants, and then you'll have a double-way arrow for equilibrium. So the base on the reactant side of the equation and the conjugate base on the product side, and that's how you're going to determine your one-way or your double-way arrow. So HBr, is it one of your big six? Yeah, so this is a strong acid, right? So it's going to completely give up its H plus and donate it to the water. So we get H3O plus and bromide. So this is my conjugate base, and this is a base, right? Which one is stronger, this or this? Has to be the one on the left, right? Because this is a weak base, because this is a strong acid. So basically you have water and bromide competing for protons. Water is the stronger base, so it wins most of the time, and the reaction goes to completion. Winning means that it is going to accept the hydrogen better than the bromide would. Because bromide is a very weak base because it comes from a very strong acid. If this had the ability in the solution, right, all four of these components are in the solution. If this were stronger than water, then this would pull the H plus to it, and then it would go back and create more reactants. Weak acids. So ammonium is a weak acid. It's not one of our big six, so we just identify it weak. So this is the acid, base, conjugate acid, conjugate base. So I have two pieces, the base and the conjugate base. So since that's a weak acid, then this is a strong base. And then this strong base is going to accept the H plus most of the time, and it's going to drive the reaction back to the left and create ammonium. Make sense? All right, what determines the strengths of different acids? Some acids are stronger than others. Obviously, we have our list. So what makes those stronger? If you notice on there, I have HCl, HBr, and HI on the list, right? If you're looking at your halogens, we have 3 out of the 4 halogens creating a strong acid. But why is HF not on that list? There's a specific reason, and so that's what we're going to look at, is their ability to lose their protons, their hydrogens. And it always has to do with the force of attraction between elements. So we're going to look at almost, sort of, Coulomb's law and electronegativity when we're determining the strength of an acid. So acid strength increases when moving down a group. If it's a binary acid, what does binary mean? 2 elements together. One of them is going to be the H because this is an acid, and then the other one's going to be the anion. So if you start going down the group, what do we know is true about the halogens? As you go down the group, what increases for periodic trends? There's a whole bunch of things, but radii, right? And so if you think about what's holding them together is the nucleus. This is sort of going back to all the way from the beginning, atomic structure. Your nucleus and your electrons. And your electrons on the other atom are there. They're sharing them because these are covalent bonds. They're sharing them. But if your nucleus is really far away from the other nucleus, it doesn't have as strong of a force of attraction, right? But if they're really close together, then you have a really strong force of attraction. Something that is a strong acid can willingly give up its H plus and just get rid of it. That's a strong acid. It gets rid of its H plus. A weak acid holds on to its H plus. So if it can willingly get rid of it, then it's going to be considered a stronger acid. So look at the strength. HF is weak because look how small fluorine is. Fluorine is going to readily hold on to its H plus because it has a strong force of attraction there. So think Coulomb's law in terms of distance. And then as the distance between H and Cl increases, it can kick off its hydrogen, HBr and HI. So out of these, HI is the strongest acid because it can get rid of its H plus so easily. Understand this? You will 100% get theory questions I will ask you about which acids are stronger and why. You're not discussing electronegativity here, are you? You're discussing your distance. So the greater the distance between the nucleus of the anion and its outermost electrons, the smaller the attractive force on the H+, and the easier it is to get rid of it. Conjugate base strengths of binary acids. So conjugate base strength decreases when moving down a group. So when you're thinking of a base, what should you be thinking of? Its ability to Gain or accept a hydrogen. So think of it reverse now. The one that has the greatest ability to accept a hydrogen should be small or large? Small, because the smaller it is, its nucleus is closest to the other things on the outside and can easily attract it in, right? So fluorine, being the smallest, can attract a hydrogen the easiest, and therefore it's the strongest base. But we already discussed this, that a weak acid has a strong conjugate base, a strong acid has a weak conjugate base. So if I just showed you in this slide that this is the strongest acid, then it is the weakest conjugate base, right? Because it's so big that it has a hard time attracting the H plus to it. And then as I get smaller and smaller and smaller and smaller, now I can attract an H plus to me easier. So HF, in terms of bases, is going to be the strongest conjugate base out of this. Understand? So you should write a note to yourself about it. Well, it's kind of right there. The smaller radius has the ability to attract or accept H plus ions. And that's what a base does. All right, oxoacid strength. I think we're just going to get through these 2 more slides, maybe 3 more slides, and then we'll stop there. We're going to stop at oxoacids. All right, an oxoacid, as the name would imply, is an acid that has oxygen, right? And what is oxygen? If we're thinking about oxygen on periodic trends, we usually say that's pretty electronegative, right? So now we're going to compare electronegativity. Oxoacids are not binary, right? So I'm going to have always, if I'm considering an acid, I'm talking about its ability to dump its hydrogen, to get rid of its hydrogen. So an OH group bonded to an element that is not bound to other oxygens, this is your first type of oxoacid. HOI, Y can be anything, any constituent group here, or it could just be another element, like HOCl or HOBr. It can be an OH group bonded to an element that is bound to other oxygens, HYO, and lots of other oxygens. So this is surrounding it. So clearly in this situation, this is more electronegative than this situation, right? So would this or this be a stronger acid, considering we don't know what Y is? So what does a molecule have to do to become a strong acid? Get rid of its H+. Here's the H+, right? Okay, so if we're thinking in terms of electronegativity and polarity and pull of electrons, you're going to have a big old pull of electrons in this direction because of all the electronegativity. Whereas this, you're going to have a mediocre pull of all the electrons due to electronegativity. So the greater that pull away in that bond, it's going to dump that hydrogen much easier. So the electronegativity here causes that to dump. So we'll look at each of these. The acid strength for an oxoacid that doesn't have multiple oxygens on it is going to depend on its electronegativity of what Y is. Whatever Y is will pull the electrons furthest to it. So what's your strongest oxoacid? HO what? HOF. Because fluorine's the most electronegative, so it's going to pull the electrons out of this OH bond and dump your hydrogen. So this makes the oxygen a little bit positive. This weakens the bond between O and H plus breaks off easily. What does it mean when it says it makes it a little bit positive? We know that when we draw electronegativities, we say this is slightly negative and this is slightly positive because the electrons are headed in that direction. So if electron density is moving away from something, we say that it becomes slightly positive. So therefore, it's going to dump that. So HOF is the strongest acid. So there we have your increasing acid strength. HOF would be next, but it's not up there. Oh, the last thing I wanted to say here about Ka. So we know, we didn't really talk about Ka yet, but Ka just means products over reactants. But we know that this is going to be the dissociated H+. So if Ka is increasing, that means that it's making more H+, right? That's what Ka, we'll get to that though specifically in a different lecture. But if your dissociation of your H+ makes more and more and more H+, that's a product, then your Ka value will go up. All right, next type of oxoacids are the ones that have lots of oxygens surrounding them. So the more oxygens you put on it, the greater the electronegativity, and then the easier it is to dump that H+. So increasing the number of electronegative oxygens increases electron density around Y. This reduces the electron density between the hydrogen and oxygen in the OH bond, and it dumps its hydrogen. So the only thing that I've noticed in years past that students get confused with is when I compare different types of acid strength and I ask you to justify, you're not sure whether to justify it using distance or electronegativity. If it's a binary acid, like HF, HCl, HBr, HI, you're using distance. If you're looking at an oxoacid, you're using electronegativity. Don't confuse the two. You know I'm going to ask you that. All right, carboxylic acids, same exact idea as before. This is still an oxoacid. Carboxylic acids are a very specific type of functional group. They're attached to lots of different molecules. R is any functional group on the outside. It could be anything. It could be a long chain. It could be literally anything. It could be a cyclic structure. But this portion is considered the carboxylic acid. They're generally weak acids, but you can increase the strength of a carboxylic acid depending on what your R group is. So again, it's going to dump the hydrogen because of the electronegativity pull there. If your R group becomes more electronegative, then it becomes a stronger acid. So that's exactly what I just said. What is this structure? You know this. Acetic acid, right? But this is some other acid, again, carboxylic acid group, but it's attached to CF3. Well, all of these fluorines attached to it are much more electronegative than the hydrogens attached to the acetic acid, so the pull is in this direction much stronger than the pull in that direction, and it will dump the hydrogen more easily. Okay, that's where we're stopping. Good? Okay, so now we're going to look at the math calculations, which is primarily what we're going to focus on throughout this entire section, is just how to calculate everything. So what we're going to look at for the rest of today is just how to calculate pHs and how to calculate the concentration of H+. So we'll get to the slides, but basically a pH measure determines how much H+ is floating around in a solution. So if H+ is available, it means that it is either acidic or basic. I mean, everything has some sort of pH unit on it. It's either acidic or basic depending on how much H+ is floating around. So we're going to look at that, but the first thing we have to determine is that we're always pretty much looking at aqueous solutions, aren't we? I mean, it's very rare that we're going to have a non-aqueous solution. So in water, water itself dissociates into H+ and OH-, right? We just saw that. So the autoionization of water we have to take into consideration when determining pH. What autoionization means is that it automatically ionizes into its ions, right? H2O is a molecule, and then it dissociates into H+ and OH-. This happens automatically in water, but to a very, very small degree. So its Kw value is really, really small. What does W stand for? So the equilibrium of water, Kw, is really small. Think of all the Ks you have. Can you see how important equilibrium is in this course? Like, you've got to get it. So now we have Kw, which is a determination of how much H+ is floating around. So remember, when we use K expressions, we don't include solids and we don't include liquids. So if we're starting with water, and it's just saying like water plus every water that's floating around in that beaker can dissociate into H+ and OH-. Now remember I told you yesterday that H0+ is the same thing as H+. It's just that I'm attaching it onto a water to make it the acidic hydrogen. So impure water at 25 degrees C, this is key. So water will ionize and have a greater ionization at different temperatures, just like we know that equilibrium will change at different temperatures, right? Your K value, temperature depending on if it's an endothermic or an exothermic type of reaction, if you increase the temperature, this could change basically your K value. That's the only thing that changes Ks, right? So if I tell you that the K value is 1 × 10⁻⁴, this is specific at 25 degrees. So it's telling me that the concentration of H0+ is 1 × 10⁻⁷, and OH is 1 × 10⁻⁷, and the concentrations are equal to each other, so the solution is neutral. So that's where we're going to get our pH from. What do you think a neutral pH is? 7. And we're going to look at how to calculate that. So this equation is really important that you memorize this, because if you know the concentration of one of these components, then you can solve for the other because the Kw expression is always the same. It's 1 times 10 to the negative 14th. So you have to memorize that. You have to know that. And that'll help you solve for all the other concentrations. I mean, this is going to get incredibly advanced when we look at all the other calculations we're going to end up doing. But this is sort of fundamental and will help you figure out the rest of your problems. So if you know one concentration, you can find the other using the Kw expression. This is what I just said. Okay? Memorize it. It's useful, blah, blah, blah. So let's try and utilize it. So take your calculators out. The concentration of hydroxide in a solution is found to be 1.4 times 10 to the negative 11. Find the concentration of H3O+. So you're literally just going to set this up. You write your expression. So Kw is equal to the concentration of this times this. So it's essentially 1 times 10 to the negative 14th divided by 1.4 times 10 to the negative 11th. And then you calculate your H+ concentration. You good with that? And then always is helpful is to rearrange your equations to show the setup before actually solving. All right, same thing that I've been saying. You're going to end up writing your expressions. You always write out your reactions. You're going to choose to either write it with water or without water. Both of them are identical. So if you see me writing it in the second expression, hey, let me pause this. All right, so we're going to start Ka and Kb, which what do you think that means? Starts with an E. Equilibrium of acids and bases, right? So if you haven't noticed, equilibrium is incredibly important for AP Chem. You have to do it for all sorts of different topics. So we're going to do Ka and Kb, same thing though, always products over reactants. We don't include liquids and we don't include solids. But in this case, we'll definitely have some sort of equilibrium. If it's a really strong acid or a really strong base, we assume complete dissociation, and so we technically have a really, really, really large Ka or a really, really, really large Kb, right? And then we're going to look at the pH of weak acids and bases. So that's kind of tricky, because right now, how do you solve pH? You do directly this, right? And then you say, all right, well, whatever she gives me as the concentration of H+ is going to be the pH, right? Except now we know if we have a weak acid, it doesn't completely dissociate, right? So we have some of it remaining as the acid with the H attached to it, and then some of it dissociates to H+, right? We'll have to figure out how much dissociates into H+. Because remember, pH is always how much H+ concentration is floating around. And then polyprotic acids we probably won't get to today. That just means that they can give off more than one H+. All right, so the first thing is our acid dissociation constant Ka, and it's always equilibrium system. Now they can give you, I think last year they gave an equilibrium question, and they made it seem like you needed to do an actual equilibrium expression and calculate and solve, but really if you look at your Kas and the numbers are really, really large, then that's telling you that you have 100% dissociation, right? So pay attention to what your values actually are. But if we're solving for Ka, you're going to do the same way as before. Products over reactants. We don't include liquids. We don't include solids. If there's coefficients, what do you do with them? You raise it to the power. You make it the exponent, right? So for this one, this is our acid dissociation constant. Strong acids have a Ka value too, so even though we have a strong acid, you know this is one of your big six, it has a one-way arrow. Remember that you can write it with H2O, but you could also just write it as HCl, one-way arrow, H plus Cl minus. It's still going to be the exact same Ka setup, but it would just look like this. So this is just sort of the shorthand way, but it's still going to have the same exact K. So you do end up with a Ka value because it still is products or reactants, but we would assume that there's almost nothing left of this. So it's completely product favored, and so you would have a really large number of your species in that solution. So I just want to point out when you're finding, this is really important, when you're finding a Ka, you have to start with an acid. I know that seems ridiculous for me to even say, right? But you're going to get to a point where I'm going to give you base reactions instead of acid reactions, but I only give you a Ka value. So I can relate Kas and Kbs together, and I'm going to show you how to do that in a second, but recognize that the reverse of this reaction is a base picking up an H plus and coming to an acid, right? And then the the HCl is going forward. This is the acid. If I started this and I wrote this in the reverse direction, then this would be starting with a B, right? A base. So I just want to point out that if you're going to use Ka values, then write an acid reaction. You can't start with a base and use a Ka value. These are all the little things that I'm saying should be on like a notes page somewhere because you're going to have to pay attention to these details. All right, so here are some acid dissociation constants. Obviously, HCl is a really strong acid. It has a really large Ka value. Nitric acid, large Ka value, but not nearly as large as HCl. 30, and then we get to some of these which are smaller, so these are our weak acids, right? So again, I'll touch on this eventually, but this can behave both as an acid or a base because it can pick up an H plus or lose another one. So this has a low Ka value, lower, lower, lower. So the lowest Ka values are going to be the ones that are the weakest acids. So down here, hydrocyanic acid is the weakest of the acids. So you're just going to look at acid dissociation constants to tell you which acids are the strongest. You have to just make sure you remember to do that. So the larger the Ka, the stronger the acid. All right, so a base dissociation constant. So this is what I was saying before. You can use Ka values, but then you write an acid reaction. If I'm going to use a Kb value, then I need to start with a base reaction, right? So use Kb values, then write a base reaction. That means that you have to start with the base. So bases are always going to pick up an H plus, right? Acids are always going to give off the H plus. So if you're starting with the base reaction, you write NH3. Again, you don't necessarily have to add the water there, but without the water, it's kind of hard to see where you would pick up the H from. So a lot of students just include water all the time because it just makes it easier for them. So NH3 picks up the H plus to make NH4 plus and then OH minus. And so it should be products over reactants, and you're starting with a base reaction, so then it will be your acid over your base. All right, so same thing with your Kb values here. So a very, very large Kb value indicates that you have mostly products, right? And then that means that it's a really strong base. Ammonia, NH3, is not a very strong base. ClO minus, do you remember that one? What's the name of that polyatomic ion? What? Hypochlorite, right? Because chlorate is ClO3 minus, ClO2 minus is chlorite, ClO minus is hypochlorite. And then you should pay attention, right? Anytime that we have these nitrogen-containing compounds, even though you're not familiar with them, what should you recognize? Nitrogen has what on it? If you were to draw the structure, it has a lone pair. So if you're not sure, then I guess you could draw the structure, but just pay attention. Anytime you see a nitrogen-containing compound, likely has a lone pair. If I'm going to turn it into the acid, then I'm going to add the H on it, and I'm going to put a plus sign. That's what you do. It picks up an H. So you would just add the H. Like here, I probably would write it here, H3NOH, and then put a plus sign on it. So when you're adding H's, they get their plus sign. In this case, it wouldn't because it's already a negative. You would add an H plus, and it would just cancel that negative. Same thing here. You add the H plus, it becomes positive, so NH4 plus. So the stronger the base, the larger the Kb. All right, pKa and pKb values are often given. So they'll give you a question, and instead of giving you the Ka or the Kb because you need it, they'll give you the pKa or the pKb. But P of anything means what? negative log. You can find the P of anything. I can find the P of Mrs. De Bruin, the negative log of Mrs. De Bruin. Whatever it is, just P means negative log. So if I want to find pKa, it's the negative log of the Ka, so the same thing that you did yesterday, if you want to find the Ka value, you're going to take 10 to the negative pKa to solve for the Ka. You need the Ka because you can't figure out the equilibrium, any of the concentrations of the ions, without the Ka value. So you're going to have to find the pKa and the Ka and how they're associated. Same thing with pKb and the Kb. All right, so what I wrote up here for you before is that we can solve for the Ka and Kb by using Kw. It's just basically saying these acids and bases dissociate to give us the K of water at 25 degrees. And then another thing that you should know is that the pKa plus the pKb is equal to 14. So you can kind of go back and forth with those numbers as well. And again, you'll end up choosing which way you want to go for these to solve for them. It's sort of like how you could choose here and here, which way you want to go. But they all those equations work. All right, so find Ka at 25 degrees C for hydrocyanic acid with a pKa of 9.31. So if you're given the pKa, you can just set this up. Ka is equal to 10 to the negative pKa, and then you plug in your pKa value, which is negative 9.31. All right, so reverse of what you did, same thing with pH. If you have your pH, you take the decimals, and the decimals become the sig figs. If you have a pKa, you take the decimals, and the decimals become the number of sig figs. So because this has 2 decimals, then it needs to have 2 significant figures in the Ka value. Same thing with pH, right? pH has 2 decimals, then the H plus concentration would have 2 sig figs. So make sure that you pay attention to that. So this is our Ka value. It's really low, which means that HCN is a weak acid. Got it? Right? That's how we can pay attention to the Ka values. All right, so if you take a look at all of the pKa values here, what do you notice about the smaller the pKa? The stronger the acid, right? So you have to sort of associate that. We already said if it has a really large Ka value, large Ka values are going to mean that it's a really strong acid. But if you take the negative log of that, you're going to get a small number. So the smallest numbers are going to be your strongest acids. Think of it the same way with pH. The pH scale makes a lot of sense, right? You know really low numbers are very acidic. Well, for something to be very acidic, it has to have really a lot of H plus in it. And that would have a very strong acid. So if you're taking negative log of H plus, a lot of H plus would give you a very low pH. If you take a Ka and you take the negative log, a very big Ka will have a very low pKa. All right, so same thing as before, you're just looking at different Ka values to determine the strength of the acid, and then the smaller the pKa, the stronger the acid. Everybody good so far? That kind of stuff, I mean, maybe just memorize that, but you understand K is products over reactants. So if it's a big number, it has to mean it's product favored, which means it's a strong acid. All right, same thing with pKb. Sodium hydroxide has a very large number, gives you a negative number. Then ammonia, a weak base, and then going down the list, we have weaker bases, and then the pKb value goes up, the weaker the base. All right, so your relationship between Ka and Kb. So here's the basic reaction. So this is what I was talking about up here, right? If you have a Kb, then you need to write your reaction with a base. So this is a base. Kb reacts, well, goes in water, pulls off the H plus from the water to make ammonium, the acid, and then the conjugate base, right? So this is base, acid, conjugate base. I write my Kb value to be my products over my reactants. If I were to write the opposite of this reaction, I would write NH4 plus goes into water. Not plus OH, but NH4 plus goes into water. This is the acid. So the acid then is going to donate its H to the water. This becomes the conjugate base, and then this is your conjugate acid. If I were to write the Ka reaction, it's NH3 times H3O plus over NH4 plus. So these values are the reverse of each other, right? The reversed reaction. So you have to be super careful that if I give you a Kb, that you don't write a Ka reaction. And you're going to see that on a bunch of problems, because I could give you, say, this reaction, but just give you a Kb value just to mess with you, because that's what the AP exam would do, right? That just means don't use the Kb value here. You need to use Ka, and that's where you're going to go and use this equation to solve. So the next slide, I'm going to show you how they come up with that. So this is the first one is your what? Ka or your Kb setup? How to be your Kb, this first one, right? Because this is your reactant, products over your reactants. So this was your Kb, this is your Ka. So look what cancels, right? And it's just the concentration of OH times the concentration of H plus gives you Kw, which is what we did yesterday, right? So then if I want to know what my Ka and my Kb, it's going to be the same exact thing. It's equal to 1 times 10 to the negative 14th. So this is just showing you a whole bunch of equations mixed in here, but it's essentially what I just wrote. Kw equals Ka times Kb. If we take the log of each of these, then the pKw is equal to the pKa plus the pKb, which pKw is 14, because negative log of 1 times 10 to the negative 14 is 14. So pKa plus pKb equals 14 at 25 degrees. Or we can say this concentration, same thing as before, pH plus pOH equals 14. I gave you that yesterday. So all of these are really helpful. Some of them are on your equation sheet, some are not. You okay with that? All right, calculating pH for strong base solutions. Pretty simple, we did this yesterday. Find the pH of a 3.5 molar sodium hydroxide solution. I added this sort of in earlier today, we already saw this. So since it's a strong base, we assume complete dissociation. If you wanted to find the pH of it, you have to recognize that you're actually finding pOH first, right? Or you can do what? If you're given the 3.5 molar sodium hydroxide, what's the other approach? You just did this. Well, I'm saying you could use this. Where did I put it? You could use this to find the pH, right? But you first have to find, or you could use this and then this, right? There's two different approaches. So this, or you could take your this and find your pOH that way. So whatever approach you want to do. All right, so since it's a strong base, we can assume complete dissociation. So it goes from 3.5 molar sodium hydroxide is actually 3.5 molar sodium and 3.5 molar hydroxide, right? I always suggest that you write out your reactions because some of you, like today on the Quizlet, you just missed that this was going to be doubled when I gave you that calcium hydroxide. So if this is 3.5, then this is 3.5, then this is 3.5. So in this example, we just took the pOH is negative log of 3.5. You get the pOH, and then 14 minus that is going to give you the pH, which is 14.54. So sort of to what Mike was saying earlier, you can extend beyond the pH scale for something that's very strong, either acid or base. Yes? All right, so now we're going to look at our pKa and our pKb values. An acid was dissolved in water, and the pKb value associated with its conjugate base was found to be 15.5. All right, so notice that this is sort of tricked already. What did you dissolve in water? An acid, but it's giving you a pKb value, right? And a pKb value just tells you about its base, not about its acid. So the conjugate base has a pKb of 15.5. What did we learn already about that? So low pKbs are strong bases. So since this is a high pKb, its conjugate base must be a weak base, which means that the acid must be strong. Get it? Did you follow that all? So I always say be smart before you start because you should think about that stuff. That should sort of make sense to you before you're starting a problem. All right, so what's the pKa value for this acid? What are you going to do? Easy approach, right? That's why I say you have all these things here. Yeah, so you're just going to subtract, right? Go ahead. So because we said we should have a very strong acid, what should the pKa be? Really low, right? And it is. We get negative 1.5. Correct? Because 14 minus 15.5 gives you a negative 1.5. So this must be a very strong acid. I keep repeating this, but is the solution acidic or basic? Clearly acidic, right? Because, well, our pKa tells us that it's a strong acid, but it already said an acid was dissolved in water, right? Is the conjugate base a stronger or weaker base than water? So what's the thought process there? So first of all, what is this, a one-way arrow or a two-way arrow? A one-way arrow. So whatever our acid is, it goes into water, and this is our acid, and this is our base, and then we get a conjugate acid, which is going to be the H3O+. So this is your conjugate acid. And then you're going to get some base, so I'm going to call that, A-, right? Because this would have been HA, whatever this is. So this is my conjugate base. So is the conjugate base a stronger or weaker base than water? The conjugate base has to be weaker, right? If it were strong, then it would be competing for the H+, and it would rip it off of it and drive it back to the left to recreate that acid, wouldn't it? And then if that's true, then that would be a double-way arrow, and we would have a weak acid. But because this is a strong acid system, it completely dissociates the H+, and then water and A- are competing, but A-, since this is a strong acid, this has to be a weak base, right? We've already clarified that, but you can think of it in so many different ways too, about competing and one-way arrow and a strong acid and all that. Make sense? Okay. Find the pH of a 2.5 molar solution of HF. All right, so this is, we've just switched. Your mentality has to now recognize if this is a big 6 acid or not. So if you don't know your big 6s, it's impossible for you to move forward, right? Because all you would do now, if you assumed this was a big 6, is you would just find pH directly like we've been doing. Can you do that? No, because HF is a weak acid and it doesn't completely dissociate. And remember, pH is a measure of how much H+ is in the solution, right? We don't know how much H+ is in solution because we didn't assume complete dissociation. So now you have to use equilibrium to solve. So this is a weak acid, it turns into the acid in the base, and it gave me a pKa value. So if I want to find pH, what do I need? Here's your equation. What do you need? Concentration of what? Every time they ask you for pH, you need to somehow find H+ concentration. Somehow. It's going to be a whole variety of ways to do that, right? You might be given a base reaction, and you find OH concentration, and then you have to kind of do this thing and find pH again. But you're always looking for H+ concentration for pH. So if I have here a weak acid, they gave me my pKa value, right? Essentially, what I'm looking to do eventually is come up with H+, and this could be H3O+ or H+, times F- is over the concentration of HF. That's eventually where I'm trying to go, because then I can solve for this piece, right? And remember with equilibrium, when we did this, we came up with ice charts and all, we did all that. We'll do that again. But that should sort of be familiar to you of how you solve for this. This becomes x squared over 2.5 equals some Ka value, and then we solve for x. Same procedure every time. All right, so first we need a Ka because we can't plug in pKa. So how do you find Ka from pKa? 10 to the negative pKa, right? So since the pKa has 2 decimal places, how many sig figs should I have? 2. So plug that into your calculator, right? We cannot leave that as the expression. You can't write 10 to the negative 3.14. You actually solve for it. So when you're done, check that you got the answer. So we got 7.2 times 10 to the negative fourth, right? So that right there is kind of also indicating that you have a weak acid because you have a low Ka value. All right, so now we're going to solve for H plus by plugging in essentially this expression here. So let's just kind of relive Rice charts. It's going to be, right, your whole reaction is here. I'm going to put the arrow in so you see it. We dropped water because water is not part of it. So if we're calling this a Rice chart, that's what it is. Our initial concentration of HF is what? 2.5, right? What's H plus and F minus? 0. So how much does HF go away? Minus X, and H plus and F minus increase by plus X. And then we solve for our equilibrium, which is X times X over 2.5 minus X. You remember this whole thing about quadratic equations and how we'll never have to use them? So what do we assume that little minus X is? It's what? Negligible. Meaning that this is such a weak dissociation that we're not really concerned about how much of it is going to convert or go away. So we're just going to eliminate it. So what is the rule about eliminating?
Larger than 10 to the
Yeah. And it will be, right? It's always going to be. But you can solve for X and then go put it back into your expression and make sure that it didn't change your Ka value. That's really the easiest technique rather than trying to memorize numbers. All right, so now we're going to put this into our Ka expression. So H plus, F minus, HF. We get rid of our little x because we assumed that it was negligible. And then we're going to solve for x squared. Okay? Make sure you can do this in your calculator. All right, so you solved for H plus, but the question is specifically asking you to find pH, right? So now you're just going to plug that into your negative log of the H plus concentration. And then because your concentration had 2 sig figs, then your pH should have 2 decimals, 1.38. So I just want to point out here, we do have, perhaps you would assume, a low pH. But when we were looking at, say, like hydrochloric acid, the pH was negative. It can be. And I want to just point out that the molarity of an acid doesn't indicate the pH. So I could have a 2.5 molar hydrochloric acid, and I could have a 2.5 molar HCl. What determines the strength of an acid is how much H plus is floating around, right? So if HF doesn't dissociate very much into H plus, it doesn't matter that it was 2.5 molar. It just matters how much of it is actually going to go into the H plus, okay? Moving along. Find the pH of a 1.5 molar HCN solution given your pKa here. So similar approach, you're going to solve on your own this time. I'm not going to guide you through that. I bet you can get through it to the end. Okay, so let's just flip through. Ka was 4.9 times 10 to the negative 10. 2 decimal places gives you 2 sig figs. Ice chart should read this. You plug it all in. pH is 4.57. You got the correct decimals? Okay. I guess we'll stop there. So we'll look at some homework over the weekend.